Hello again. Hopefully we can finish. Actually, no, we are going to finish chapter 3 in this video. I hope you're doing well. So let us get started. We want to finish chapter 3 by going over implicit differentiation. So we know about differentiation already. If you've been watching the videos in chapter 3, at this point you should be able to differentiate any function. Well, not exactly. There are a few more maybe functions we're going to talk about, and those are coming up. But for now, let's talk about implicit differentiation. What is it? Well, if you have a function like y equals to f of x, this is explicit function. Why? Because it's explicitly given. That means we are given that y is a function of x, and we know the rule of the function right here, right? So when I write y equals to x squared minus x plus 1, I know exactly how y is related to x. This is how it is related to x. So the output and the input, you have explicit relationship between them given here, right here. But sometimes we assume that there is a relationship between variables. So in an equation like this, we can assume that y is a function of x. That means if we have y equals to some kind of expression, whatever, right? If we substitute that in here for y, then we get an equality here. That's what we assume sometimes. But if somebody wants to find the rate of y with respect to x, here is easy to do. You already know how to do that. The rate is 2x minus 1, right? But what is the rate with respect to x here, if we assume y is a function of x? Okay, so now you might say, okay, if we have something like this, let's say x squared plus y squared equals to 4, then I can actually solve for y, right? And I say, okay, y could be, you can think of y as two functions maybe. It's we're going to talk about the fact that actually you can write more than two functions for y for this to work. But let's say these two functions, right? Then you take the derivative. Okay, but how do you do that if you have an equation like the one I have given you here? How do you solve for y? It's very difficult to solve for y. But we are interested in knowing the rate of y with respect to x, right? And that requires a different type of differentiation, and that's implicit differentiation. That means without really breaking down into many functions in terms of y, can we find dy dx? And the answer is yes. So implicit differentiation allows us to find the slopes of tangents to curves that are clearly not functions, right? They fail the vertical line test. If you graph this, you see that is not a function. All right, so here is an equation, x squared plus y squared equals to 25. Well, everybody knows from algebra and pre-calculus that that is an equation for a circle that has center 0 and a radius 5, right? That's what that is. And obviously is not what? Is not a function, right? Now we can solve y for y and write it as a function. Now if we want to do that, then we can think of many different ways that we can define a function out of this equation, right, for y. For example, we can define a function to be negative square root of 25 minus x squared if you solve for y, right? So let's look at different types of functions that we can talk about. So here's a circle. Now remember, function has to pass what? Vertical line test. So we can consider this part to be a function, like that. Or we can consider this part to be a function, would be plus the square root of 25 minus x squared. Or, so you could be, the function will look like this, or a function will look like this. Or we can define a function this way, get that quarter and this quarter, and define a function like that. Or define a function this way, get this quarter and this one. Because this part is not included here, right? You see, they pass vertical line test, right? And they all represent functions that come from this implicit equation, right? So let's look at different type of functions we can define. In fact, if we click over here in the notes, you can click here and go to a GeoGebra online under my account somewhere right here, and now you can see right here. So let it download. Here it goes. So I'm going to turn these off. You can have one at a time. So here is one way we define a function right here. That's a function. So we can define it to be a square root of 25 minus x squared when x is between -5 and 0. That means that part. And be negative square root of 25 minus x squared otherwise. That means over here, right? So that's one way to define a function out of that equation. Another way is, let's say, this way. So we define it to be positive square root of x, square root of 25 minus x squared for this domain values. And then otherwise it's going to be here. Or we can define it this way as just a positive square root of 25 minus x squared from -5 to 5. Right? So we cut the bottom part. Or we cut the top part and we get this. Right? So 4 different ways we can actually think of a function coming out of that equation. Right? All right, now assume y equals to f of x such that when we substitute f of x into xy equals to 1 for y, we get an identity. Now there is a difference between an identity and an equation, right? For example, when we write 2x minus 1 equals to 5, this is an equation and it's true for x equals to what? 3, right? If we write an equation like this, x squared minus 4 equals to 0, this equation is true for two numbers, x equal to 2 and x equal to -2, right? But when we write something like this, that x plus y squared equals to x squared plus 2xy plus y squared, this, even though we use equation here, but really is an identity. So we can put another line here, another segment, and this is identity. So that means this side equals to this side for all values of x and y. Equation is only true for some values of x, of the variable, but an identity is true for all values. So we assume that what we are dealing with here, when we are given an implicit equation like this one, we assume that there is a y as a function of x, that if we substitute that rule for y, then this would be an identity. That would be true, right? So, so except maybe some numbers that make the denominator 0, we can exclude those, but for any other number, right, this would be true. So here we assume that y is a function of x. Of course it is, because we can solve for it easily. Y equals to 1 over x for x not equal to 0, right? Then xy is an identity. So since we are assuming that y is a function of x, we can use the product rule to take the derivative of both sides of xy equals to 1, right? So remember, the product rule, if you have uv, you want to prime it, is u prime v plus uv prime. Now here, the difference is that we're going to think of y as a function of x. So that means when we want to find the derivative of it, we have to be careful and use chain rule. So here you go. What's the derivative of left side? Well, it's going to be derivative of x times y. Derivative of x times y. I use Leibniz notation here. Derivative of x times y plus derivative of y times x equals to, what's derivative of 1 with respect to x? 0. So that derivative of x with respect to x is 1, right? So 1 times y is y, plus x times derivative of y. Well, we don't know what y is, so we have to leave it as derivative of y, right? So it's like y prime equals to 0. And from here we can isolate dy dx. So x times dy dx equals to negative y. So dy dx is negative y over x. But we know what y is. If we can solve for y, we can put it there. Otherwise, we just leave it like this. That's the derivative. The difference is that now we have two variables in the derivative, and that's okay. But if we can solve for y and substitute for it, then we can put it here and we get this, right? It would be the same thing if we just take the derivative of this, which is negative 1 over x squared, right? If we directly take the derivative of y equals to x to negative 1, right? Y prime is going to be negative 1 times x to negative 1 minus 1. So that's negative 1x to negative 2, which is negative 1 over x squared, which is the same answer, right? Of course, in this case, we could do this because we could solve for y. But remember, if you're given something like, like this one, it would be really difficult to solve for y, right? All right, so let's see. So if it is not always easy to solve for a function defined implicitly of an equation, fortunately the technique of implicit differentiation allows us to find the derivative even though we have the implicit form. So if we want to take the derivative of x squared plus y squared equals to 25, first of all, what do we mean when we say take derivative of both sides? We mean take the derivative with respect to x, right here. We could take the derivative with respect to some other variable, but for now, the derivative is with respect to x. That's why this notation is better than just writing f prime, right? Because it tells you exactly what the variable of differentiation is. Okay, so let's do that. So we want to take the derivative of this side and set it equal to the derivative of this side, right? So now one more thing I want to mention before we continue is that if we have an equation, right? If we have an equation, let's say we have something like this. If you have an equation, it is not true that derivative of left side equals to derivative of right side. That's not true, because derivative of this side equals to what? Equals to 2, but derivative of this side equals to 0 and is not equal. So when we say take derivative of both sides, we assume that this is not an equation, but is what? But is an identity, right? Now identity, this works. If you have an identity, let's say I'm going to give you an example of an identity. Here is an example of an identity, right? So what is the derivative of this side by chain rule? It would be 2 times x plus 1 to the first power times the derivative of inside, which is 1. What's the derivative of this side? Well, it's 2x plus 2. And notice that that's the same thing, right? So if we are dealing with identities, we can take the derivative of both sides and get away with it. But if you're dealing with equations, that's not actually true. Okay, so we assume we are dealing with identities, so we can take derivative of both sides. So derivative of this side with respect to x equals derivative of this side with respect to x. What is derivative of x squared? What's derivative of something squared? Well, derivative of something squared is 2 times something to the first power times the derivative of inside, which is x. Well, we don't usually write it. In this case, I write it just to make sure we understand. We are using chain rule. If you take derivative with respect to x, then derivative of x with respect to x would be 1, and it is just 1. What's the derivative of something squared again? Is 2 times something to the first power times derivative of inside, which in this case we have to write it because we don't know what y is. So we have to write it as derivative of y with respect to x. What's the derivative of a constant with respect to any variable? Is 0. Constant doesn't change no matter what the variable is, right? And now we solve for dy dx. Right, we move this is just 2x, goes to the other side, becomes negative 2x, and then divide by 2y on both sides, we get this, which simplifies to negative x over y. So dy dx is negative x over y, right? That's what it is. Now, if you want to find the slope of the tangent line at any given point to this graph, which is a circle, right? So you want to find, let's say, slope of the tangent line to this circle at this point, then you would have to have what? You would have to have 2 numbers, x and y, right? To find the slope of the tangent to this curve, you need 2 numbers. All right. So, so note that the resulting expression is in terms of both independent variable and the dependent variable. So in some cases we can substitute, but in general you don't have to and you can't. So here is the example we started with. Can we now find, first of all, you don't know how to graph this, I understand that. In fact, it's not that easy to graph something like that, right? No, Isaac Newton tried to categorize some of these, like the ones to the second power, the ones to the third power, and all that combination of x and y. And he came up with like 73 different categories, and he missed few. So they're not easy to actually graph these, but with the power of technology, we can get an estimate of the graph. And as I said before, these things are, we assume that these are real numbers, but of course real numbers include irrational numbers. So you cannot really graph for every number between this number and this number. There's no way, because some of them are irrational. So what the computer does basically is approximating all numbers to be rational. And then if you zoom in, of course, these are just pixels, right? So there are empty spaces between them. So the real graph, really, what you're looking at is this. There are a bunch of points like that. But since we can't tell, well, that's okay. It's like quantum mechanics. What really is going on is not really classical physics. But for macro world, when things are the size of human beings, you know, they're not at the atomic level, the classical physics, Newtonian physics works. And it gives us equations, and we can, you know, use them, apply them. But the real story is really quantum physics, which is kind of weird when you study it. It's very interesting. And so that's the idea of graphing. Graphing is really cheating here, but it works for all the applications that we want to apply calculus to. All right, so what is the slope of the tangent line to this curve, which looks like this if you graph it, and at this point, at 1, 1. Now, notice that even figuring out, if you're given that x is 1, and you want to find y, what y is, if I put a 1 here, put a 1 here, I'm going to have to solve a 6-degree polynomial to find out what y is, right? So that's why I gave you x and y here. So you don't have to worry about that. So all we have to do is apply implicit differentiation to this and find dy dx, isolate it, and then put these two numbers for x and y and find the slope of this line, right? So here we go. So take the derivative of this side with respect to x, take the derivative of this side with respect to x. What's the derivative of x to something to the 8th power? Well, that's 8x to 7th. I'm not going to put dx here because that's 1, right? Okay, that is a product rule. That's a product, right? What's the derivative of that? It's the derivative of this one times that, and the derivative of this one times that. So let's do that. What's the derivative of x to the 6th? It's 6x to the 5th times y to the 4th plus derivative of this times x to 6. So derivative of this is 4y to the 3rd times derivative of inside, which is dy dx, times x to 6, right? So all of this here is just that, derivative of that. What's derivative of something to the 6th power? 6y to the 5th times derivative of y equals to derivative of 3 is 0. Okay, now dy dx shows up in two places. The rest of this is algebra to isolate dy dx. Move all of that to the right side, right? And then factor dy dx. You get dy dx on here. When you factor it, you get dy dx times 4x to the 6th, y to the 3rd, plus 6y to the 5th. And that goes in the denominator. I trust that you understand how I got from here to here. That's just algebra. If you don't see it, stop the video and isolate dy dx yourself, and you see you get this. Okay, so that is the slope. That's the derivative in terms of x and y. So to find the slope, so the notation is this notation right here. Remember before we had dy dx, and we put a little segment and we put x equal to, let's say, for example, 1 equals to something. But here, since we have two variables, we put a point here, 1, 1, like that. So this indicates that x is 1 and y is 1, and we're going to substitute those numbers here for x and y. And if you do that, if you put a 1 here, 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 you're going to get negative 7 over 5. Okay? Again, you can stop the video and make sure you get that. So that would be the slope of what? Of this line. Now, to write the equation is easy because we have a point. So that's x1, y1. So x1 goes here, x1 goes here, and y1 goes there. And that's the slope of the line. So that's the equation of that line, right? And here is another example. Find the equation of the tangent line to this at the point -1, -1. Use a calculator or computer software to graph the function and the tangent line. Okay. Well, it's not really a function here to graph the equation, to graph the relation. Maybe I should do that now that, well, I could do it. Here we go. Let's do it. There you go. So we were right here. Since we are here, why not? There you go. Graph the relation. And the tangent line to it. Okay, there you go. So now you can use GeoGebra to graph these things. So let me show you how quickly, since we are here, and there you go. So I'm just going to put that equation x to the 4th power times y minus x times y to the third power equals to -2. There. Okay, so notice that the GeoGebra, right, you see, GeoGebra graphs it for you, and you see it's not really that easy to graph, right? It's lots of points, but GeoGebra graphs it, and you can point on a object right here somewhere. Let's put it there, and then let's graph a tangent to it, tangent line. To graph a tangent line, you pick the point and you pick the object, and it graphs it, and grab the select button and move it over here. So what we want to do is this right here. Was it -1, -1? I guess, was it? Let's see. Yeah, it was -1, -1. So what we wanted to do was to find what? The equation of this line, and notice the GeoGebra gives you the equation right here. 5x plus 4y equals to -9. That's the equation of this line, right? All right. Now, you could break this down into a bunch of functions, right? You could, but that would be difficult. Not impossible for this problem. It's not impossible to do it for this problem, but it would be very difficult. Okay, so let's continue. So we're gonna do it, of course, algebraically using implicit differentiation. We're gonna take the derivative of both sides again. This requires a little practice. There are some common mistakes, forgetting that y is a function and not considering y prime. So instead of using Leibniz notation this time, I use just Newton's notation. So I use y prime instead of dy dx. So here, what's the derivative of that? Is derivative of this times derivative of y. I mean derivative of this times y and times plus derivative of y times that. So derivative of x to the fourth is 4x to the third times y plus derivative of y, which is y prime, times x to the fourth. And then this one is minus, don't forget, we have to find the derivative of this product, and then you have to distribute the minus, right? That's another common mistake, so make sure you don't do that. So derivative of x is 1 times y to the third plus derivative of y to the third is 3y to the second y prime times x, right? Derivative of -2 is 0, right? So the rest of this is now isolating y prime, right? So we have to isolate y prime. Move this to the other side that doesn't have y prime. This one doesn't have y prime. We move it to the other side. And now you see we have y prime in common here. We factor it out and then divide by that expression to get y prime by itself. So now we have y prime as an expression of x and y, right? So what do we want? We want the value of this at -1, -1. Which we substitute and do some arithmetic. We get -5/4, and now we have what? A point and a slope. We can write an equation, right? That is the equation of that line. The GeoGebra gave us the equation in the form of ax plus by equals to c, standard form. I could have converted it to this form, but I didn't, but we have it here. All right, so now I want to talk about derivative of exponential and logarithmic functions. This is the part that was missing. After this, we are able to take the derivative of any type of function, okay? So let's talk about that. In order to find the derivative of exponential function, first of all, in algebra, you learn about exponential functions, something like that. But remember, in algebra, we said b is not 0 and is not 1 and is not negative number, right? And we defined it in algebra. We defined exponential functions and then defined logarithmic functions to be the inverses of exponential functions, right? In calculus, we start with we're going to start with this and see if we can take derivative of this, right? So how do we take derivative of b to x? B is a number, as I said, from algebra. B is any positive numbers except 0 and 1, right? So, what's the prime? What's the derivative of any function? Well, derivative of any function is going to be f of x plus h minus f of x divided by h, right? So we apply this to this function. So it would be b to x plus h minus b to x over h when h approaches 0. And then you know that if you have a b to x plus h, we can write it as b to x times b to h because the exponents get added, right? So now we take the b to x out and we get this. And notice that all of these have h in them. B to x doesn't have an h in it. So we can put the bx out of the limit, b to x. We put it out of the limit. And then we get stuck because we don't know what to do with this. Remember, these limits always end up being what? 0 over 0. So we have to do something about this h, right? And that requires a little bit of work, okay? So let's go over that. And once we know what this is, then we are ready to take the derivative, okay? All right, so let's do that. So we have to make some certain assumption. Now, these assumptions actually, to understand them completely, we need to get into number theory and a little bit more mathematics. So we're going to limit our scope to calculus 1. And for that reason, I'm just going to give you the basic assumptions we make and we move on. Okay? If you're interested, you can do some research yourself about this, especially if you want to major in math. Maybe you're interested in knowing. But for now, let's look at the basic assumptions. So the basic assumptions we make are these. We begin with the assumption that the function b to x, b greater than 0, is defined for every real number and is continuous and is continuous. So in algebra, we learned that by definition, b to 0 is 1, b to 1 is b, b to negative m is 1 over b to m, b to m over n is nth root of b to the mth, right? But one thing that we kind of got away with in algebra, and probably your teacher didn't mention it, was how to do something like this. What does that mean? 2 to a square root of 2. Because you can't really do it, right? Can you do this? No. Because definition of 2 to a power means you write 2 that many times and then multiply. We can't do that. Well, we can't do it here either. That's why we defined it to be 1. We can't do it here either. That's why we defined it to be b. We can't do it here either. That's why we defined it to be 1 over b to m. We can't do it here either. That's why we defined it to be this. But what do we do with this? And that's what we're going to talk about. Well, we don't know what b to square root of 2 is, right? But we know that we don't know 2. Let's take 2. So we don't know what 2 to the square root of 2 is. What's 2 to the power square root of 2? We don't know. But we know a square root of 2 is what? Is 1.414213, right? So this continues forever and never ends because it's an irrational number. But we know for sure that this number is between 1.41 and what? 1.42. Do you agree? This number is in here. So we are going to say, okay, square root of 2 is between these two numbers. That means whatever 2 to square root of 2 is has to be between what? 2 to 1.41 and 2 to 1.42. And if you do that, you get these two numbers. So this is 2 to 1.41 and this number is 2 to 1.42. So we know this is somewhere between these two numbers, right? Now, in practice, irrational numbers are always approximated. Irrational numbers are used in pure mathematics but have no applications. There is no way you can build a table that is the square root of 5 by square root of 5 feet. There is no way you can do that because the square root of 5 is an irrational number. You can't measure the square root of 5 and cut it. When you cut it, you're cutting a little bit of it, and just the dust would make it not being square root of 5, right? So they may represent something about the universe that we still don't know, maybe discover in the future, but for now, or maybe nothing at all. Maybe it's just our imagination, our wrong interpretation of nature. We don't know. But for now, let's make sense of it this way. So by assuming that the continuity of this function, remember we assume that this is continuous, right? And b is positive. We may interpret b to irrational number to be this limit. Limit of b to x when x approaches rational numbers, right? So remember, if we want to approach, so if we want to know what, for example, let's say what's 4 to a power of x is, we're going to end up with what? We're going to end up we're going to end up with a value like pi. What is 4 to pi, right? How do we do that? Well, we can think of 4 to pi. Now, pi is like 3.1415 and so forth, right? So we can keep adding decimal places to 3.14154 pi, and for every decimal value that we put there, right, we get a value for 4 to that power, right? So if we do that, if we think of 4 to pi to be 4 to x, the limit of it when x approaches those rational values, we're going to get this table below, right? So that's 4 to 3, right? And then 4 to 3.1, 4 to 3.14. So we keep adding what? Those little numbers, right? And obviously, if we go to 4, the approximate answer the calculator gives is 77.88023, right? So we are somewhere over here. So this is what? This is too big, right? So it's like going, here's pi. So we approach it from left and approach it from right. And we see what 4 to that, and these are rational numbers, right? When we approach pi, we go only to the rational numbers, to the left and to the right. And if we do that, we see what 4 to x is approaching. And here you see this is to the right of it, and this is to the left of it. And the actual value is somewhere between this number and that number, right? Because here we passed it. The actual is like 0.88023 with the approximation the calculator does with 14 decimal places. So the actual value is between these two numbers, right? We approach it from right, we approach it from left, and we get these values. So that's the idea. It may not make sense, but it's practical and it works, right? So in order to find the derivative of it, for bx equals to b2x, we make the following more assumptions. First of all, we assume that this function is defined for every real number and is continuous. Now, when we say it's defined for every real numbers, we mean the x, not the b. b is positive, right? And so b prime at 0 exists. We assume that at 0, this has a derivative. The rate at 0 exists. Again, we assume that. There is a unique value of b. There is a number that we can substitute for b here such that when we take the prime of that and then evaluate it at 0, we get 1. Okay? And that number turns out to be a very famous number, e. So there is a base that if you use that base, the derivative would equal to 1 at 0. All right. Now, again, it's a little vague here, but it's going to work. So here is the graph of bunch of exponential functions with different b values, right? You see, with different b values. And notice that if we do this and kind of eyeball the slope of the tangent at 0 to these graphs, you see the one that gives you the slope closest to 1 is e. So this number, and this number turns out to be, that means the base, let's just put a number, the base that gives us the prime of this at 0 equal to 1 turns out to be between 2.7 and 2.8. So we're going to call that number e, and we're going to call this function with the base e of x, e to x. Very useful number in mathematics. And then we're going to define the inverse of this to be log base e, or ln of x. That's the inverse of this. So that's the exponential function, and the inverse of it is ln x. Okay? And it's called the natural logarithm. This is natural exponential function, and the inverse of it is a natural logarithm, ln x, which is right here. Okay, so here, again, I'm going to take you to that website, GeoGebra website. And what I'm going to do is this. I'm going to wait for this to load. And looks like it's loaded now. Okay. So you see, if I change this base right here, that's the base of exponential function. The derivative of that function at 0 will, which is the slope of the secant basically, because we don't know the exact value, right? But if I go really close to 0, like this close to 0, and find the slope, which is approximation of the slope of the tangent line, I'll get these numbers here. Right? This is the slope at 0. And notice that if I change that base, notice the slope right here changes at 0. And remember, what we're looking for is a number that gives us the slope of what? The slope of 1. And if I go to the left, maybe, that's too slow. So let me go to the close to it, approximately right about there. You see that's, let me see if I can go right and get it to 1. It takes a while because, you know, I use 0.00001, right? And now I have to wait for all of these numbers to turn 9, so I'm going to move it quicker. There. So somewhere between these two numbers is the exact value we're looking for. We can never get the exact value, right? But that's the mysterious or just mathematical number e, right? You see that? Right there, we're approaching e. Right here, we're approaching 1. So the number we're looking for, that is the base of the exponential function that gives us the derivative of the tangent line 1 is e, right? So this estimated value is called e, right? Which we can never get to it, but we're going to call it e. So that's a number that gives us what? Gives us the derivative at 0 to be 1, right? And we assume this number is between these two. If you want to be more precise, you can add some more decimal places. Well, you can never get to it. We assume that this number exists, and that number, if it exists, it would for sure make the derivative at 0, 1, right? So that means our limit now becomes what? E to x. If we want to take the derivative of e to x at 0, it would be f of what? Instead of f is e. So it would be e of x plus h minus e of x divided by h. Now remember, our x is 0 here, right? So we can do it this way, or you can do it with this definition. E of x minus e of a over x minus a, and x approaches a, right? Now in this case, x is, a is 0, right? So put 0 here, put 0 here, put 0 here, what do we get? Well, we get e of x minus e of 0 divided by x minus 0, right? And that's the idea. So here x approaches what? Approaches 0 here. All right? Because remember, in this case, x has to approach a, and our a is 0, right? So x approaches 0, and that's what we get. So that's the derivative if we use the base e, right? So what is that? Well, let's see. So to find the derivative, so let me go back here. So derivative at 0 that we were looking for, with this base, derivative at 0 would be what? So if we use e, then derivative of e to x at 0 will be 1, right? So if we go back to the trouble we had over here, right? And remember, we got to this point and we got stuck, right? So the derivative equals to this, and that's where we got stuck. So now we say, okay, if we use e, right? If we use e, then b prime at 0 here, right? B prime at 0 would be the same as e prime at 0, which is what? Which is 1. So to find b prime of x, we need to know b prime at 0. And again, if you use the base of e, that would be 1. So derivative of e to x, so if we write e of x equals to e to x, we end up with what? We end up with a 1 here, because this would be e prime of 0. And this would be e to x, right? All of these would be e, right? And the answer would be what? Would be just e to x. So that's the idea. So you see I have it here. So if we consider e to x, e of x, which is e to x, then we end up with this, right? And now limit of this when h approaches 0, that's the definition of what? Derivative at 0. And derivative of 0, we just found out, we can assume this to be 1. So the most interesting function in mathematics is this function whose derivative is itself, right? Derivative of e to x is itself. So if we have f of x equals to e to x, the derivative of it is just itself, right? The easiest question in the world, whose answer is itself, right? You know a question like that? And the answer is the question itself. All right, so y equals to e to something. So instead of putting x, we can put something there and use chain rule. So derivative of e to something is e to something times derivative of something, right? Maybe it's easier to look at it this way. What's derivative of e to u? Is e to u times u prime, right? All right, so let's now go back to procedural stuff. What's the derivative of that? Well, what's the derivative of e to something? Is e to something, right? What's the derivative of e to something? Is e to something times derivative of something, which is 12x to the third. That's it, we're done. What's the derivative of e to something? Well, it's e to something, right? Times what? Times derivative of this, which is by itself chain rule. What's the derivative of tangent something? Is secant squared something times derivative of something. Isn't that something? Yes. So we just multiply these, right? 2 goes before everything else. And then this is e to tangent 2x, and then secant squared 2x, right? That's the answer to that. Derivative of this. All right. So a colony of mosquitoes has an initial population of 1,000. After t days, the population is given by a of t. Show that the ratio of the rate of change of the population, a prime of t, to the population a of t is constant. Okay, so we have an exponential function here with the interesting base of e, right? That number that is kind of between 2.7 something, right? So here you go. So we take the function that gives the rate. That's the population at any given time. And the time is number of days, right? And we start with 1,000. That's the initial value. When t equals to 0, this would be 1 times 1,000, so it's just 1,000. We start with 1,000 and it grows. How do we know it grows? Because the power is positive here. So what's the rate? The rate would be, we keep the 1,000. What's the derivative of e to something? Is e to something times derivative of something. What's the derivative of 0.3t? It's 0.3. That's it. So that's the derivative. Now we are told to find the ratio of the derivative to the function itself. So that means we have to take this and divide it by the function itself, which is that, right? And then after simplifying, we see is a constant. So that means if you divide the rate of change by the function, we get constant. We just proved it. All right. If x is greater than 0 and y equals to ln x, what's the derivative of the inverse of e to x? Remember we said if you consider e to x to be the exponential function, its inverse is ln x, right? So what is the derivative of the inverse? Well, remember we can use our idea of inverses and chain rule. So here is y equals to ln x, right? So if you write y equals to ln x, I can take e to both sides, right? On the left, I get e to y. On the right, I get e to ln x. They cancel each other because they're inverses, so I get x. So e to y equals to e to ln x. That means e to y equals to x. Now, this is an implicit form of y as a function of x. So we take the derivative of both sides with respect to x. What's the derivative of e to something? Is e to something times derivative of something. Equals to derivative of x is 1. So y prime is 1 over e to y. But what is e to y? E to y is x, so we put x there. So that's the derivative of ln x. Now notice that 1 over x of course has 2 branches, but we don't need this because x is what? Positive, so we just use that one. So that red one is the derivative of ln x. So at any given point here, let's say over here, what's the slope of that line at 1? Well, it's 1, right? And so forth. All right. So if instead of x we have ln u, right? What's the derivative of ln u? Well, that would be a derivative of ln something is 1 over something times derivative of inside, which is u prime, right? All right. So here you go. What's the derivative of ln something? Well, 1 over something, right? 1 over something times derivative of something, which is 20x to the 4th, right? And that's it. What's the derivative of that? Well, we can do that, but notice that we're going to get a kind of tedious algebra here, right, to deal with. So what we are going to do, we're going to change the form of this, so we don't have to deal with a lot of tedious algebra. How do we change the form of it? We're going to use what? We're going to use properties of logarithm. We know that if we have a ln of a to mth power, that's m ln a, right? And also we know that if we have a ln of a over b, this is nothing but ln a minus ln b, right? So these are properties of logarithms you learn in algebra or pre-calculus. So let's do that. So we're going to break this down first, like this, and then take the derivative. Because remember, if we don't do this and take the derivative, you have a tedious algebra to deal with, right? We're going to get the derivative. What's the derivative of ln something? Is 1 over something, right? It's going to be all that, and then times the derivative of something, which involves the quotient rule. It's a lot of algebra. So no, we don't want to do it that way. So what do? We break it down using properties of logarithm. Now we take the derivative. What's the derivative of 2 times something? Well, we keep the 2, and we take the derivative of this. What's the derivative of the something minus something? Is derivative of something minus derivative of something. What's derivative of ln something? Is 1 over something times the derivative of something, right? And then the same thing for the other side. What's the derivative of ln something? Is 1 over something times derivative of something. And if the rest of this is algebra, you put this together, you can stop the video and make sure you get from here to here. But that's just combining 2 fractions with common denominators, right? So, so what else? Well, let's do another one. Here we go. So let b be greater than 0. What is the derivative of b to x? Because we couldn't do that. Remember, we started with this, and we said, okay, we assume is e to x and take the derivative of it. And we got itself. But what if it's not e, it's b? Okay, well, we're going to write it like this. You say y equals b to x. Well, we can take ln of both sides. So ln of y, right? ln of y equals to ln of b to x, right? Just half here. And ln, as I discussed right now, right, 30 seconds ago, ln of a to m is m ln a, right? The power rule with logarithm. So we can bring the x downstairs. So ln y is x times ln b. Now this is something we can take derivative of because we know what the derivative of ln something is. What's the derivative of left side? Is 1 over something times derivative of something. What's the derivative of x times a number? What is the number? It's like, what's the derivative of 3x? Is 3. What's the derivative of ln b, which is a number, times x? What's ln b? And now we isolate y prime, multiply both sides by y. And what is y? Y is b to x. So the answer is b to x times ln b. So that means if we have an exponential function with base e, the derivative of it is itself. Derivative of e to something is e to something. Times, of course, derivative of something, right? So derivative of e to x squared, right, is e to x squared times 2x. But derivative of e to x is just e to x, right? Now what is derivative of, let's say, 3 to x? Well, that would be, again, itself, but times ln of the base. That's what we found. So the new formula we have for exponential functions with the base that is not natural, e, is itself, but what? We have to multiply by ln b. And you see, for example, derivative of 2 to x is going to be what? Derivative of 2 to x is, what's the derivative of 2 to x? Is 2 to x times ln 2, which is that red one. Now, if this blue one was e to x, derivative would be exactly itself, right? But if it's not e, derivative is a little bit off, right? All right. So what's the derivative of 2 to something? Well, it would be 2 to something times ln of 2 times derivative of something, right? So derivative of 2 to something is 2 to something times ln 2. That's the formula. And then by chain rule, we also have to multiply by this, which is derivative of the exponent. The rest of this is simplifying. Differentiate this. Well, that's a quotient, right? So think of this as u, think of this as v. So the answer, if this is u, right, and this whole thing is v, then the answer is uv prime is going to be u prime v minus uv prime divided by v squared. And if you follow that, that's u prime. U prime is the prime of 3 to x, which is 3 to x times ln 3, right? Times v, which is that, minus u, which is that, times derivative of this. Derivative of this is derivative of 3 to x plus 0. Derivative to 3 to x is 3 to x times ln 3. And then divided by v squared. We're done with calculus. The rest of this is simplifying, right? Obviously, you see, if you distribute this, you can cancel these two, and you end up with this. You stop the video and make sure you get this. All right, so what is the derivative of log base b? We know derivative of ln x or ln u, but what is the derivative of log base whatever? Not just e, whatever, right? And to do that, we are going to exponentiate both sides with base b. So what do? We do b to this power, and then b to that power. And notice that b to the power of log base b of x, they cancel each other, so you end up with x, right? So you have b to y equals to x. We just learned how to take derivative of this, so let's use it. So what is derivative of b to y? Is b to y times ln b times derivative of y. Because here is not b to x, it's b to a function. So you have to take that into account by chain rule, right? And equals to derivative of x, which is 1. So y prime is 1 divided by this whole thing, right? So that means derivative of ln u is 1 over u times u prime. Derivative of log base b of u is still 1 over u, and it's still times u prime, but you have an extra ln b in the denominator, right? See that? That's it. Of course, if this is x, you don't need this, right? Because x, derivative of x is 1. Now, that's one way to prove it. Another way to prove it is to think of what? Think of this. Change the base. We know in logarithm, we can change the base of this as ln x over ln b and use quotient rule to prove that the answer is this. And you can stop the video and make sure you get from here to here. This is just a little quotient rule and algebra. All right, so what is log base 5 of 3x squared? Well, derivative of log base 5 of something is 1 over something times derivative of something. Also, in the denominator, we're going to have ln 5 in the formula. And that's it. And these are the graphs of this. This function is defined for all values of x except for 0, right? Because negative values would make this positive is still valid. So the derivative is that red one. All right. So find the slope of the line tangent to the graph of this at 1. So basically what we have to do is take derivative of this and evaluate it at 1. So this is the derivative, right? Derivative of log base 2 of something is 1 over something times derivative of something, which is 3, and also divided by multiplying the denominator by ln of the base. Now what is this at 1? If you substitute 1 here, that's what you get. Now that's the slope. So what do we find? Well, that's all we had to do actually. It says find the slope of the line. You don't have to find it, but here's the equation if you want it. So you see that's the graph, that's the tangent to it, and that's the equation of it. Because if you put 1 in here, you get log base 2 of 4. Log base 2 of 4, what's log base 2 of 4? Well, remember, logarithm is, the question we are asking here is, what exponent of 2 gives you 4? Well, 2. 2 to the second power is 4, right? So it's 2. And then x value is 1. So we are finding the equation of the line at 1 and 2. And the slope of it is what we found here. Okay. So the derivative of x to x, what is that? We don't have any formula to find that. Common mistake is to say the derivative is x to x minus 1. No. The power formula doesn't work here, right? So in this kind of differentiation, we are going to use logarithmic differentiation. How? We're going to say, okay, we want to find the derivative of y equals to x. We're going to take ln of both sides, right? Why? Because now you can bring down the x using properties of logarithm. So ln y is x times ln x. Now we take derivative of both sides and isolate y prime. That's the trick we use. So derivative of left side, what's the derivative of ln something is 1 over something times derivative of something. What's the derivative of a product? Is derivative of x times that, derivative of this times that. So derivative of x is 1, derivative of ln x is 1 over x. So 1 times ln x plus 1 over x times x. So that's it. So y prime equals to, well, you multiply both sides by y. But what is y? Is x to x. So the answer is x to x times ln x plus 1. Very different from this wrong answer, right? That doesn't make sense. Okay, so, and that's the graph of it. That's x to x. And this is the derivative of it. All right, so using logarithmic differentiation, let's look at this right here. It says differentiate this, right? If you were to differentiate this, it would be really difficult even if you use all the rules that we learned, right? This is a quotient rule. This is a product rule in the numerator. There's a product rule in the denominator. That's a big algebraic mess, right? But what if we use logarithm? We take the ln of both sides, right? And then ln of something over something is ln of something minus ln of something, right? Properties of ln. And then ln of something times something is ln of something plus ln of something. And minus ln of something times something is ln of something plus ln of something. And then we distribute this minus. So that is what we are going to take the derivative of. Instead of what? Instead of that. That process is called logarithmic differentiation. So let's take derivative of this, which is 1 over y times y prime equals to, what's the derivative of this? 1 over x. What's the derivative of this? Well, the derivative of ln something is 1 over something. Remember, there's a 1/2 here. We keep it. And then 1 over something times derivative of something, which is 2. And the 2 cancels that 2, so we just get that. Minus derivative of x is 1. What is that? Derivative of this is 1 over something times derivative of something, which is cosine x. We have a 3. See, we have the answer. All we have to do is take the both sides and multiply both sides by y. But what is y? That. You see, what a big mess would have been if we didn't use logarithmic differentiation. That means this is the answer we're supposed to get. If you were to do product and quotient rule and didn't make any mistakes, you would have come up with something like this. But notice that we only wrote like few lines and we got the answer. So that's called logarithmic differentiation. Extending the power rule, now we can say that the derivative of x to n is nx to n minus 1, no matter what n is, whatever number, right? Not a function, but a number. So we said that we started this chapter with n being positive integer or 0, and then we said n could be negative integer, then we said n could be a fraction. Now we say that n could be any real number, right? Or how can we prove that? Well, here's how we prove it. We say, okay, let y be that, take ln of both sides. By now, you know we get this, right? And then take derivative of both sides. What's derivative of ln y? Is 1 over y times dy dx. What's derivative of r times ln x? Well, we keep the r because r is a number. What's derivative of ln x is 1 over x. And then we multiply both sides by y, which is that. And what do we get? The formula. So x to the power of some number prime is that number, x to that number minus 1. If that number is the square root of 2, right? If that number is the square root of 2, it doesn't matter. We still get what? The same formula works. Okay, so now, like for example, this right here is nothing but pi times tangent to pi minus 1 times derivative of tangent, which is secant squared. Okay? All right, so finally we got to the end of this video and chapter 3. And I'm going to go back here and say hi and bye until the next video. Okay?